Today we're diving into a paper called Thinking with Programming Vision, towards a unified view for thinking with images, which introduces a new framework called CodeVision.
And we have to start with a pretty critical, almost shocking vulnerability they found in even the best state-of-the-art multimodal large language models.
Well, ones you're probably using every day.
Exactly. The core finding is that they are just surprisingly brittle. We're talking about simple, real-world image changes, like a basic 90-degree rotation or just flipping it horizontally.
Yeah.
That can crush their performance on tasks like OCR by up to 80%.
80%. That is a massive failure point. And CodeVision's solution is, well, it's a fundamental shift in thinking.
Yeah.
Instead of these rigid pre-registered tool names, they propose a code-as-tool framework.
Right, so the model itself is actually generating executable code. That code becomes the universal way it interacts with the image.
Which solves so many of the scalability problems.
It really does. And the model is trained with this really clever two-stage method. First, supervised fine-tuning, or SFT, to learn the basic language, the syntax. Then that's followed by reinforcement learning using a new dense process reward.
And this doesn't just fix the brittleness. It fosters these really advanced behaviors like chaining different tools together, generalizing to tools it's never seen, and even recovering from its own errors.
The bottom line is that the CodeVision models set a new state-of-the-art. They nearly doubled the performance of top competitors, even Gemini 2.5 Pro, on some really tough new benchmark.
Okay, let's really unpack this, because for anyone building or deploying MLLMs, this brittleness to simple image changes has been a quiet nightmare. So why did the tool-augmented systems we had before fall so short?
We have to start with those diagnostic results because they frame the whole problem perfectly. The researchers did something very simple. They took an image, applied one of 5 transformations, like a 90, 180, or 270-degree rotation, or a flip,
Right.
and just asked the MLLM to identify which one was applied.
A task that is completely trivial for a person? I mean, we'd all get 100%.
100%. But the models. GPT-5 got around 50%. Gemini 2.5 Pro was down at 33%. And this isn't about some complex reasoning. This shows a fundamental weakness in just handling orientation.
So if it can't even tell an image is upside down, its ability to, say, read text off that image is obviously going to be destroyed.
It's critically compromised. When they took those same simple rotations and applied them to standard benchmarks like OCRBench, the model's performance just plummeted, sometimes by that 80% figure we mentioned.
Wow.
So this proves that tools for things like rotation aren't just a nice to have. They're mandatory for any kind of real-world robustness. And beyond that, the paper really targets 3 specific structural limitations in how we used to think about tools.
Okay, what was the first one?
The first is what they call the marginal necessity of tools. Most of the old benchmarks focused on the crop or zoom tool, but the performance gains were tiny, maybe 2 to 5%.
So not really essential.
Not at all. Sometimes a model trained with just basic RL and no tools could match that performance. The tasks just weren't hard enough to force the model to learn to use the tool properly.
So the model basically learned it could get by with its raw vision, and the tool was just this optional extra. For CodeVision, they needed tasks where you literally cannot succeed without it.
Precisely. The second limitation was a lack of flexibility and scalability. Current systems are built on this really brittle idea of a tool registry. You manually define a tool, like crop, with specific arguments.
And if you want to change that name, maybe from crop to region select.
You have to retrain the entire model. It's a developer's nightmare. It just kills any ability to generalize or adapt to new tools.
Okay, so they're brittle and inflexible. What's the third limitation?
Limited multi-turn, multi-tool composition. Most systems could only call one tool at a time or maybe do the same action over and over, like cropping multiple times.
But real-world problems aren't like that.
Not at all. A real problem might require you to, say, rotate the image first, then maybe enhance the contrast because the lighting is bad, and then crop a tiny piece of text. That kind of strategic sequence was basically impossible before.
So, to sum it up, brittle, inflexible, and couldn't chain different tools. And this is where the CodeVision solution, this universal interface, just elegantly solves all 3 at once.
It really does. The whole idea is to replace that rigid tool menu with a programming interface. So the model's output isn't some fixed API call, it's executable Python code. Instead of predicting tool name rotate degrees 90, it just predicts image.rotate.
I see the parallel to how some models use Python for math problems. It frees the MLLM from these handcrafted APIs. But I have to ask, if the model is just generating arbitrary code, What about the risk? Isn't that a bigger security risk? Or what about latency and runtime errors?
That is a fantastic and crucial question. And yes, there is a latency overhead. You have to run the code in a sandboxed environment. But the trade-off is absolutely worth it for the sheer power you gain. And that sandbox is key for security. You only expose verified libraries.
Okay.
The best part is that those unexpected runtime failures you mentioned, they actually turn them into a feature.
Right.
And that's one of the 3 huge emergent advantages of this whole approach.
All right, let's get into those advantages then.
So through their really principled training, they unlocked 3 key behaviors. First, the emergence of new tools. Because the model is talking to a programming environment, not a fixed menu, it starts spontaneously calling tools it never saw in training.
All right, so
Things like grayscale, sharpness, or edge detect, it just discovers them and uses them when they're helpful. That's real generalization, not just memorizing a list of commands.
that's incredible. What's the second advantage?
Efficiency via tool composition. Since it's writing code, it learns to chain multiple operations into a single step. It might combine a contrast enhancement and a grayscale conversion into one line of code and run it once. Much more efficient.
And the third advantage is the answer to my risk question.
Exactly. Robustness and error recovery. The system actually feeds the model the runtime error messages, the Python traceback, and the new image after the code runs.
Ah, so it gets feedback.
He gets direct feedback. It can try something, get an error, read that error, and then correct its own code and try again. Or like in one example, it tries flip horizontal, sees the result is still wrong, and then decides on its own to switch to rotate 90.
That ability to see the outcome of its actions and course corrects, that's genuine agency.
It is. But training a model to do that, to generate reliable code in such a huge action space, sounds incredibly hard.
So how do they actually approach the training?
This is where the methodology is really elegant. It's a critical 2-stage approach. Stage 1 is what they call cold start supervised fine-tuning, or SFT. The whole point of SFT is just foundational. It's to teach the model the basic grammar, the syntax of calling tools, the conversational patterns. You can't just jump into RL. The action space of code is way too big.
And they were really smart about how they built the data for this stage, right? They basically forced the model to learn the tools were necessary.
Absolutely. The SFT data was diverse, OCR, VQA, you name it. But for tasks that needed cropping, they deliberately picked targets that were microscopic, less than 0.01% of the image area.
So the model has no choice. It can't succeed with its raw vision. It has to learn to crop accurately.
It has to. They forced necessity. And they even built failure and recovery right into the training data. So they created examples where the model would get a runtime error, and it had to learn to read that error log and then revise its code.
And there's a neat technical detail here on the training, where they only calculate the loss on the assistance part of the dialogue, the reasoning, and the code itself.
Correct. They mask out the user input and the tool's return image. That lets them teach the reasoning to action sequence without the slow process of actually executing code during this first stage. Once the model knows how to talk to the environment, then they move to stage 2, reinforcement learning.
Right.
And this RL stage is where strategy and efficiency come in. They use an algorithm called ChartQAPro and augment the data with harder problems, explicitly telling the agent which tools it must use to succeed.
Which brings us to what feels like the real innovation here, this dense multi-component reward function. How do you stop a code executing agent from just gaming the system?
That's the million-dollar question. A simple reward for just getting the final answer right is too sparse. It just doesn't work. So they decompose the total reward into 3 weighted parts: the outcome, the strategy, and a cost penalty.
Okay, outcome is just accuracy. Let's talk about the strategy reward, the dense process signal.
So this is all about rewarding good tool selection along the way. The first part is rewarding the use of must-use tools. For something like rotation, it's a one-time bonus. For cropping, it's more clever. The reward is proportional to the IOU improvement.
Can you just quickly define IOU for everyone?
Sure. IOU is intersection over union. It's just a metric for how much your predicted bounding box overlaps with the true one. By rewarding improvement, they encourage the model to refine its crop over several turns if it needs to.
That's brilliant. So it learns to get closer and closer.
Exactly. And the most innovative part of the strategy reward is the suggested tools bonus. This is how they encourage emergence. They basically look at trajectories where the model used an optional, helpful tool-like contrast enhancement and compare them to trajectories where it didn't.
Ah, and if the tool using path performed better.
It gets a reward. This actively encourages the agent to discover near useful strategies on its own.
So you're rewarding it for being curious and finding better solutions. But that sounds like it could be easily exploited.
It could be, which is why the final piece, the constraint penalties, is so important. This is all about preventing reward hacking.
What's an example of that?
Okay, so the agent might correctly use rotate 90 and get that strategy bonus, but without penalties, it might just keep calling other rotation tools over and over to rack up more points, even though it's corrupting the image and will fail the final task.
So what are the penalties they put in place to stop that?
3 main ones. First, a turn limit penalty to encourage efficiency. Second, a poor reasoning penalty. This one is great. It penalizes a correct final answer if the crop IOU was terrible.
Meaning the model probably just guessed the answer from language context instead of actually seeing it in the image.
Precisely. And third, an inappropriate tool use penalty, which punishes it for using orientation tools when none are needed. And the ablation studies they ran prove this whole system is critical. If you remove the strategy rewards or the penalties, performance just tanks.
So moving on to the validation. The theory is solid, but the results really speak for themselves. They created 2 new evaluation sets just for this.
They did. The first was the transformed benchmarks. They just took standard benchmarks like OCRBench and systematically applied rotations and flips to all the images. This directly tests that robustness problem.
And the performance gain was huge, right?
It was substantial. The CodeVision 7B model scored over 73 on the transformed OCRBench. That's a 17-point gain over its own base model. It proves it can successfully fix the image before doing the main task.
And the second benchmark, MVToolBench, sounds even tougher.
MVToolBench Multi-View Tool Benchmark is a gauntlet. It was designed to require a sequence of different tools. You have to fix the orientation, and then you have to crop a region of text that is incredibly tiny. Success demands complex, multi-step strategic thinking.
And this is where CodeVision really pulled away from the pack.
Completely. On MVToolBench, CodeVision 7B scored a 60.1. That's nearly double the performance of the strongest competitor they tested, Gemini 2.5 Pro, which only got 32.6. It's just clear proof that this paradigm enables much more complex reasoning.
The qualitative examples are just as impressive as the numbers. There are cases of really sophisticated self-refinement.
Yeah, there's a great figure in the paper showing the model making an initial crop, looking at the result, recognizing it missed a word, and then executing a second, more refined crop on the next turn.
So it's not just following a plan, it's reacting to the visual output of its own actions.
And we also see that spontaneous tool chaining. There's one amazing example where the model combines 5 different tools in a single line of code, and 3 of those were emergent tools it discovered itself. It just confirms the flexibility you get from code.
The results are clear. CodeVision really does seem to address that core brittleness by turning visual interaction into a programming task. But the authors were also candid about limitations and what's next.
They were. They acknowledged that their focus was pretty narrow, mainly on orientation and cropping. The next big challenge is scaling up the diversity of tools. Imagine applying this to multi-image tasks, like comparing 2 images or merging data from different visual sources.
And they also want to refine the supervision itself, right, to move beyond just must-use tools.
Correct. They want to get to a point where the system can reward the use of beneficial tools, like maybe enhancing the contrast on a blurry image isn't strictly required to get the answer, but it's good practice. Rewarding that encourages a more nuanced, proactive agent.
And finally, it looks like there's still a lot of room to grow here. The framework isn't tapped out.
That's right. The performance curves they show are still pointing straight up. There's no saturation. It strongly suggests that scaling up the data, the tasks, and the tool libraries will just keep producing more and more capable agents.
So wrapping up, what's the big takeaway here for you, for the technical audience listening to this, who are building the next generation of visual agents?
I think this paper represents a fundamental shift in how we should think about these models. It's a shift away from a restrictive fixed tool registry and towards seeing the MLLM as a dynamic programming entity. So the question you should be asking yourself now is, what APIs does my agent need access to? Imagine exposing a complex search engine or a proprietary database or even another generative model as just another library in your MLLM's sandboxed code environment. The CodeVision framework gives you the blueprint for how an MLLM can learn to dynamically program these external services. It really opens the door to truly general-purpose agents that can program their way through almost any task you give them.